Assalamu alaikum. Hello everyone. This is my submission for the data scientist machine learning task round 2. I will walk through each of the four questions, explaining my approach clearly and confidently. Question number 1, and the outline an algorithm for finding minimum spanning tree in a distribution system. To find minimum spanning tree in a distributed system, I would use to ODS algorithm. It's specially designed for the distributed environment where each node only knows its immediate neighbor. Here the idea is simple terms. Each node is third as its own component and looks for its own weight. Outgoing is the lightest link to another component. Then those components merge through those edges to form large component. This process keeps repeating. Find minimum edge, merge and broadcast update until it all nodes become part of the single connection component. The result in minimum spanning tree and all communication happen through the local message passing. Follow-up. In in what real world machine learning scenario would you use a minimum spanning tree? In machine learning, minimum spanning tree are used in sensor network optimize feature selection and clustering. And in machine learning, MSTs are useful for feature selection and clustering, especially in sensor network and high dimension data. For example, in a sensor network, an MST minimizes communication cost while keeping sensor connected. In feature selection, it helps remove redundant features by keeping only the strongest and most relevant connection. So overall, the MST helps both optimize network efficiency and reduce complexity in machine learning tasks. Question number 2. For this problem, I would use a segment tree or Fenwick tree. Both allow run some queries and update in order of log n times, which is exactly what we need. If if I need exact result, I would go to the segment tree. It is flexible and support complex query. But if the data stream is massive and small errors are acceptable, I would use an approximate method like a count mean or sampling. Those are the fast and far more memory efficient. Follow. How would you parallelize update for distributed feature store? For parallelization, I would share the data, maybe by user ID or by the time range, and each share would maintain its own local tree or sketch. Update would follow through a message queue like Kafka, and each node would process them independently. Then predictably, we would merge particle results from each node to get the global view. Achieve order of log n performance per operation, scales horizontally and support both exactly approximate aggression, ideal for real-time analysis and machine learning feature stores. Question number 2. Text is with design and machine learning model cache. If I were designing a machine learning model cache, I would use a split because it's a self-adjusting binary search tree. Every time you access a model, that node moves to the root. So frequently used model automatically stay near are at the top of making feature looks up much faster without any extra bookkeeping. Compared to an LRU cache, a split tree adapts naturally a change access pattern but it's less predictable. While its average performance is great, some operations can take longer because of the rotation. An LRO cache by constraint provides the constant order of one axis using hashmap and linked list, but it consumes more memory and requires speed tracking. Splitting can increase latency when access are random or uniform, since we still pay the rotate cost even when no model is hot. So a split is excellent for skewed, repetitive, and access pattern, but not ideal for the strict low latency system like live prediction service. Question number 4. Given task is build a system to support efficient merging and query connected user component in a social graph. To build a system that supports merging and query connected user in a social graph, I would use a disjoint set union or union find data structure. Each user is node and age represent relation like friendship. When an age is added, union find merges those two users into the same group. When we a query and we can quickly check if two users belong to the same connected component. With the right optimization, those operations become almost constant time that where union by rank and path compression come in. Union by the rank always attach all the smaller tree under the large one, and path compression pattern is the structure by making every node point directly to the root. Together they make find and union operation extremely fast, practically order of one. So even the large scale of machine learning graphs, we can effectively cluster user and track communities and update connection in real time. That concludes my response for the data scientist machine learning tax round second round. Thank you for listening.